Today we're going to be talking about graphing absolute value functions. So before we get going, I would love it if you guys would take a second and I want you to try the Ignite at the top of the page. Let's see what you remember about graphing quadratics. Okay, so if you didn't remember everything about graphing quadratics up until this point, that is totally fine. But it's a good recap in the sense that this right here is what we call vertex form. So I don't know if you remember this, but from Algebra 1, if I go ahead and graph this, what happens is the number that's inside switches the sign and the number that's outside stays the same. And together, those numbers, when you have those parentheses like that, what happens is that actually becomes the vertex of your quadratic. And the vertex, all that means is that is just the lowest or highest point, kind of like the point where the two sides meet together. And the nice thing about it is that there's a lot of similarities between graphing quadratics and graphing absolute value functions. And we're going to look at what some of those functions are going to be in just a little bit. But before we get going, we're going to start by just graphing just the most basic absolute value equation out there. And that is just the absolute value of x. Now, to find the absolute value of x, remember, those absolute value symbols, what they do is they take any number you put inside of them, and it makes them positive. So when I'm going to go through and pick my values, for this first one, I'm going to show you how we find what numbers should go in the table. But for right now, we're going to pick like the standard 5. So like 0, -1, -2, and then 1, and then 2. And absolute value in a way is even easier than squaring because I don't have to worry about the squared part. All I'm going to be doing is I'm going to take the number inside and I'm going to make it positive. So 0, if I turn it positive, that one doesn't really have an option for that. That just is 0. -1, if I make it positive, is 1. -2, make it positive, is 2. 1, make it positive, is 1. 2, make it positive, is 2. And what you have now are the 5 standard points for any given absolute value function. Now they may move, but when you start plotting them, you're actually going to notice something kind of strange. So if I go 1, 1, that's going to show up right there. -1, 1 is going to go here. 2, 2 is going to go here. And then -2, 2 is going to go here. And you're going to notice if we were to keep going, 3, 3, 4, 4, -3, 3, -4, 4. Hopefully you're starting to notice what kind of shape is being formed. Hopefully you're not saying a U, because the U-shaped graphs are the squared graphs. These are the ones that end up having a U shape. Absolute value graphs, these all have a pretty standard form in this standard picture in the sense that these are going to all be in the shape of the letter V. There should be no curves at that bottom point. Now this point right here, still called the vertex. That terminology doesn't change. So when it's the simplest absolute value sign out there, this is what we base kind of all other absolute value functions off of. And if you'll remember from Algebra 1, this is what we call the parent function. It's kind of like, what's the simplest version of any function out there? Like, for example, if you look at the x squared graph up top, the parent function for a squared graph is this. It's the most simple quadratic out there. If I cut out all the other random numbers and all you leave is the x being squared, that right there is enough to create an absolute value. If you take out either one of those, it becomes something that's not an absolute value or a quadratic. Now though, let's see what happens when we actually go through x. Take whatever x is, add 5, and then make that number positive. Now, something that we're going to get in the habit of is I always actually find the vertex first. And it has absolute value functions have kind of that standard function. The kind of the standard form for all absolute value symbols is we have an A on front, absolute value symbol, it's going to be x minus h, absolute value symbol, and then it's going to be plus k. Okay. Now, if you'll remember, I always call these guys Hank and Kelly. Hank always lies. But basically together, these form the vertex. So whatever is inside with the x, the opposite sign of that is going to be the x coordinate. And then whatever number is outside the absolute values kind of being added or subtracted on the end, that becomes your k value or the y value. So on this one, for example, I have a 5 inside, which means my vertex is going to be at -5. And this one, there actually isn't anything outside, which just means my y coordinate is 0. And all this does is it helps you figure out where your point should be. -5, 0, this point right here, is the vertex. Now the question is, which way does it open? But that's where we're going to fill in all of our other points. I'm going to do 2 on each side, -6, -7, and -4 and -3. Now you'll notice if I plug these in, we're going to get negative, let's see, -6 plus 5 is going to be -1, which make it positive is 1. -7 plus 5 is going to be -2, turn it positive 2, which means it's going to be the same on the other side. Now I will show you how to graph these in your calculator in just a moment, but right now we're just going to stick with just picking those points. And now we can graph the rest. So let's see, we're going to be -4, 1, -3, 2, -6, 1, and then -7. Oh, nope. -7, 2. There you go. You guys can probably do a better job of this graphing. We want to try and attempt to make those pretty straight. But there we go. Now, in terms of the parent, how does this compare? Well, really the only thing we changed, right? The only thing we changed was we added a 5 on the inside. And where did the graph go? Well, vertex used to be at 0, 0, and look where it moved. It moved basically left 5. This right here, anytime you start adding in numbers in certain places, this is what we call a transformation. And I have the definition at the bottom, but this is when a graph changes compared to the parent. Okay, so like I said, for the absolute value, if you want to write this again, for us, it's all about where our numbers added. So really, this is what, when we looked at this example 2, if it moved 5 to the left, we would say it shifted left. Woo! Grab that. Really, just describing it in general, it shifted left. Now, we actually have names for all of these transformations. Every time you put a number or sign in a specific location, it creates a specific type of transformation. And if you remember these from Algebra 1, fabulous, you're ahead of the game. If you didn't though, we're only gonna stick with, there's really 5 main ones. The first of which is a reflection. Now, all of these come from that kind of standard form of it, but they're all based on vertex form, which for an absolute value function is gonna be y equals a times x minus h plus k. And again, remember hk is your vertex. Now, when we talk about this specific 5, the first one we're going to talk about is a reflection. And this is when the graph opens down. So whenever you have your absolute value, if the ends of the graph are pointed down, that's one way to tell that it has a reflection. The other way to tell is just to simply look at the a value. And the a value is just the number that shows up right in front of the absolute value symbol. So it's something that eventually we would have to multiply through or get rid of, but it's ever being multiplied to those absolute value symbols. Now, when we talk about vertical and horizontal shifts, this is when the graph shifts left, right, up, or down. Now, when we say the graph, sometimes that's hard to tell because obviously all of the points are going to move. So the easiest point to really look at is we look at the vertex. If the vertex moves basically off of 0, 0, 0, that just tells us that we're going to have at least one of the shifts. If I move into one of the main quadrants, you're going to have both. But if I move up on the y-axis or just left or right on the axis, it is possible to only have one of the shifts. But the key is that the parent function has no transformations. So the next two that we're going to talk about are going to be vertical stretches and compressions. A vertical stretch specifically is when the A value is larger than 1. Now, something to kind of keep note of is that transformations imply that something is changing. So if I have y is equal to the most basic, obviously the parent function for all absolute values is this guy. And technically there is a 1 in front. So 1 is not, if there's no number other than 1 in front, you don't have a stretch or a compression because it's not something that's like transforming the equation. It has to be something that's different. So like if you compare examples down below, number 4, if I were to ask you about does it have a stretch or a compression, our answer would be no. Because the number in front, yeah, it's a negative. Now that's different. That's a different transformation. But the number itself in front is when that number is something that's not 1, something other than 1. So when we have now specifically a stretch is when the A value is larger than 1. Now we say the A value, but just so you guys are aware, it's really the absolute value of the A value. Just because the sign in front, if it's negative, that's a different transformation. That is when it's a reflection. If the A value is negative, that has no effect on whether or not you're stretched or compressed. So if your A value is larger than 1, you're going to be a stretch. If you are an A value that's, I say between 0 and 1, it means if we have, it's usually some sort of decimal or fraction. So like 1/2, 1/3, 2/5, 8, 7, or 7/8, something like that. But the idea is it has to be less than 1. I say between 0 and 1 though, because remember, once you get beyond 0, that's your negative numbers, and that doesn't really change it. That just becomes reflected. So let's actually look at some of these. Now, if you're going to do this on your calculator, there is a way in the TI-84 to do this. So in your calculator, if you are interested, you are first going to start off by going to, you're going to go to the equals portion. So all of the graphing features, you guys know this, are at the top. So if I hit y equals, if there's anything in here, you're going to want to clear those out. There is actually an absolute value feature. Now it depends on the calculator. If you have a newer one, it'll actually give you the bars. If you have an older one, it might just say like ABS and put it in parentheses. But to find it, all we're going to do is we're going to start by hitting the math button. So you start by hitting y equals. You want to get into the graph functions first. And then without hitting anything else, you're going to hit math. And then at the top, you're going to notice there's all these menus. It's not in this first math menu. You're going to have to hit to the arrow, one arrow to the right. So really number should be this NUM, that should be highlighted. And the first option, option number 1 is ABS. This is your absolute value. So all you have to do, you can either choose to hit number 1 or you can choose just click enter. Now, if you have the TI-83 plus CE, this will actually give you the bars. If you just have a TI-84 or a TI-84 plus, I think it pops up as ABS and then it puts a parenthesis. So that's just one, it just looks different. It means the same thing. But we're going to go through and we're going to type our equation. So I got a little ahead of myself. The equation that we're typing in is 3. Then I want the absolute value. So I'm going to go math, arrow right to number 4. Enter for number 1, and then I'm going to type in x, it's -2. Now to get out of the absolute value symbol, you do have to hit to the right, otherwise it'll just keep typing inside, and then we're going to add 4. Now if you want to see the graph, go for it. You can choose to graph it, and there is your V. Now if you want to get the actual points, remember that's in the table, so if I could hit second and then graph, it'll bring me back into my table. Now, if we were going to go through and fill in that table, I would always start by choosing one of the values that is the vertex. So I actually started with finding the vertex. It's opposite of what's inside, so 2, and then whatever's outside, so 4. So I knew that my vertex is going to be 2, 4. So I'm just going to pick the values on each side. So 1, 0, and then 3, 4. And then if you look in your table, we're going to look for the ones that go with that. So at 1, it gives us a value of 7, and at 0, it gives us a value of 10. 3, it's at 7, and 4, it's at 10. And now we can go through and we can plot our points. So I'm going to go right 1, or let's see, left or right 0, up 10, right 1, up 7, and then right 2, up 4, right 3, up 7, and then right 4, up 1. And now we can fill in our B. Don't forget your arrows. Please, this graph does go on forever. We're just not going to graph everything. Okay. So now what is the A value? Now remember, the A value is just the number that's in front. So A value on this one is 3. And here's the cool part. You really only need to know these two things if you want to find all of the transformations. Because if you look at it, the A value, this tells you 3 of them. If this was a -3, then we would have a reflection. Because A isn't negative, this graph is not reflected. This graph is not opening down. Reflection would look something like this, where like the ends of the graph went down. And this one does not, that does not happen. So the A value also tells you if you have a stretch or a compression. Now, here's the perfect time to tell you that you cannot be both. You cannot be both stretched and compressed. That number, whatever your A value is, it either is going to be greater than 1 or between 0 and 1. So in this case, 3 is greater than 1. So we would have a vertical stretch, which means I can't be compressed. If my A value is a 1/3, then that would be reversed. This is an example of an A value where it's compressed, and larger than 1 would be your stretch, obviously. Okay. So we have a vertical stretch. Now let's tackle the shifts. The shifts are all told from the vertex, because we compare this point to where the parent function's vertex was. So the parent function had a vertex at 0, 0. So think about how we got to our new vertex. Well, we went right 2, and we went up 4. So I shifted right and I shifted up. So in terms of shifts, we had both. We were vertically shifted up 4, and we horizontally shifted right 2. So there are your transformations. Now what I want you guys to do, I want you to pause your video, and I want you guys to try example number 4. Okay, hopefully check your answers. Your graph should have looked something like this. Your vertex on this case ended up being at 0, -6, and then the A value was at -1. If you missed any part of that, this is a good example to ask Ms. Hardy about. But now I did want to do the transformations with you guys. So transformations, hopefully this one, the vertex, this tells you all of your shifts. Now this one, I don't shift all directions. I go left or right 0, but I go down 6. Technically my vertex really only goes down, which means in terms of my shifts, that is going to be my vertical shift. We don't have a horizontal shift. Now, the A value tackles all 3 other transformations. The first one, your reflection, that's if your A value is negative. And in this case, it totally is, but A value is definitely negative. The A value is just the number that shows up in front of those parentheses, or excuse me, absolute value symbols. So my absolute, in this case, it is negative. Now, stretch and compression. These happen if I'm greater than 1 or between 0 and 1. And this is one of those odd cases where I actually don't have either, because it's not changing. The parent function has a value of 1 in front. The value itself is what would determine if I got larger, it would stretch my graph. If I got smaller, it would compress my graph. But this one, neither of those is happening. So I actually don't have either of them. The only 2 that should have been circled are reflection and vertical shift. Okay. If you want to try some of the U-Try Nows on the next page, now is a fabulous time to do it. I will write in the answers. So pause your video and try U-Try Now number 1. Okay, that is what a U-Try Now number 1 should look like. Again, check your answers. If any of these are off, feel free to ask Ms. Hardy to go over it with you, okay? But thanks, guys. It's been awesome. I'll see you next time.